Hey Team Bio, today is probably not an intro to pH. I'm sure you've talked about it before in methods. So maybe a reintroduction to pH is a more apt title for this screencast. So we're going to be talking about pH, what it means, and a little bit about how to calculate it, but more into how to interpret it. And it's going to be important to understand pH because the pH of a solution is going to really impact how organic molecules function, especially our proteins. So for our upcoming biochemistry unit, it's going to be really important for you to understand pH. So pH. Let's talk first about something you know. Liquid water. Liquid water is composed of many molecules of H2O, all bebopping around in solution. And you know that water molecules have a positive end, a slightly positive end, and a slightly negative end, and they form hydrogen bonds with one another. Maybe I'll move this one. In solution. And these hydrogen bonds are always breaking and reforming. Something that we haven't talked about before yet is the idea that also within liquid water are going to be some ions. And these ions are composed of products of water that have broken down into its component functions. So these ions are reactive. And the concentration of these ions is going to affect properties of the aqueous solution. And the aqueous solution is just a fancy way of saying water solution. There's an O in there somewhere. Aqueous. Solution is a water solution. Okay, these reactive ions are H+, also known as a hydrogen ion, and OH-, which is hydroxide. So pH is actually a measure of the hydrogen ion in solution. In a neutral solution, any neutral solution, so if something has a pH of 7, this means that the concentration of the hydrogen ion, and this brackets, these are just a fancy way of saying concentration. So the concentration of H+ is going to be equal to the concentration of OH- or hydroxide. In an acidic solution, the concentration of H+ is going to be greater than the concentration of OH-. And in a basic solution, the concentration of H+, yes, you guessed it, is less than the concentration of OH-. Okay, how would we get in a situation where the concentration of H+ is greater than that of hydroxide? Well, if we add an acid, which is a compound that will contribute to H+ in solution, we can increase the amount of H+. So this is a compound, UND, that increases H+ in solution. So, for example, an acid that I'm sure you all know and love is hydrochloric acid. The chemical formula for this is HCl, and the structure is an atom of hydrogen that is bonded to an atom of chloride. When you put this in a water solution, the hydrogen ion will break free from the chloride ion, and you'll be left with a chloride ion that has a negative charge and a hydrogen ion that has a positive charge. This chloride is really happy in the water solution, as you know, because it can be stabilized by the positive hydrogens, positive side of the hydrogens in any water molecule. So this is a strong acid because hydrochloric acid readily gives up free hydrogen to solution, so this is going to increase the amount of H plus in solution, and we will be more acidic. Okay, a basic solution, a base is a compound that reduces the H plus in solution. So, for example, sodium hydroxide. It's the chemical formula NaOH, and it is composed of an atom of sodium bonded to an atom of oxygen bonded to an atom of hydrogen. When you put this in an aqueous solution, what happens is that, just like the chloride, the sodium ion is very, I want to make this actually a circle, is very happy hanging out with a positive charge in solution, and then the OH minus group, I did not want to do that. I guess I just have to draw it again. It's going to copy and paste the whole thing. So the hydroxide ion is now hanging out in solution with an overall negative charge on it. But also in this solution, there is going to be some free H plus. And what happens is that this free H plus, which as you know is just a proton, it's just one atom of hydrogen, is going to bond with the water. Let's see if this works. Yes. And we're going to form a water molecule plus, where did that go? Sodium with a positive charge. Okay, so in this way, this strong base, sodium hydroxide, is kind of sucking up the free hydrogen in solution and overall reducing the amount of hydrogen ion relative to hydroxide ion. Okay, so what is pH actually? pH, maybe I'll write this over here. pH is equal to the negative log base 10 of C, where C is equal to the hydrogen ion concentration in moles per liter. Moles is a big number that you'll learn in chemistry, but what I'm concerned with is that you understand that the pH is going to be, a measurement of the amount of hydrogen ion in solution. If you have a pH of 7, this is neutral. Sometimes we call the pH, where it comes from, it's the potential of hydrogen. Or also sometimes, this is how it's written in your book, the potential of hydrogen. You'll also see it written as the power of hydrogen. Okay, but this whole negative log thing, what does this actually mean and what does this look like on a graph? So you'll see here we have concentration of hydrogen ions that will be our y-axis, and then our x-axis is the pH. So overall, if you look at the trend here, as the pH, I want a straight line that's horizontal. As the pH increases, the concentration of hydrogen ions in solution decreases. This means very basic things have, as you know, a very small amount of H plus in solution relative to OH minus, and very acidic things, which have low numbers, have large concentrations of H plus in solution. Okay, so what is the scaling on this y-axis? Let's spend a little bit of time talking about that. Okay, let's imagine we have a pH of 7, something with a pH of 6, and then something with a pH of 8. If we were to say, draw some lines on our graph and say, okay, at a pH of 7, our H plus concentration is this. pH of 6, our H plus concentration is this. And a pH of 8, our, H plus concentration is this. And then we were to zoom in and actually write a scale on our y-axis here. Let's just say pH of 7 is our concentration of H plus ions is equal to X. If we were to then jump up to pH, or I guess jump down to a pH of 6, we would see that the concentration of hydrogen ions relative to a pH of 7 is 10x. So every time you move 1 point on the pH scale, you actually move a factor of 10 in terms of the concentration. So likewise, if we looked at a pH of 8, which I actually see I've kind of drawn it a little bit further over than relative to 6, so maybe I'll move this down a little bit. Okay. Good enough. This would be equal, this difference between 7 and 8 would be 1/10 x, or we could write it as 0.1 x. So looking back over here at our scale of our pH, again, if we say that this is equal to x, this would be 10x, this would be 100x, this would be 1000x, and so on and so forth. A pH of 1 would be 1 million times more hydrogen in solution than a pH of 7. And then going in the opposite direction, this would be 0.1 x, this would be 0.01 x, and so on and so forth. Okay, so that is the pH. I want to draw your attention to an important idea in the pH as well, especially when we're talking about biochemistry, is that if we have very acidic things, this means we have a lot of hydrogen ion in solution. And you need to think about the role that having a lot of free ions in solution is going to do to structures. If you have a really basic solution, you have a lot of free hydronium ion in solution. So you're going to have to think about what this will cause as well. So very basic, very acidic solutions have a bunch of free ions, either positive or negative ions in solution. Okay, that's going to come back into play in a few weeks when we talk about enzyme structure and function. So keep that in mind. Okay, the last thing I want to talk about in the screencast is an introduction to Stop Motion Studio. So this is an app we're going to be using in class to record stop motion videos of important reactions, dehydration synthesis, and hydrolysis. These reactions are fundamental reactions that either build up organic compounds in your body or break them down. You are going to be showing the dehydration synthesis of glucose and fructose into sucrose and water, and then the splitting of sucrose with water, it's called hydrolysis, into glucose and fructose. The app is pretty self-explanatory, but you'll open it up, you'll start a new project, and you'll see this screen here. I've taken you down to the nifty view of here, all the components labeled. Something that I want to draw your attention to, obviously this is how you take a photo. This is where the photos end up. You can move the photos around, but you want to be careful about that, or reinsert the camera if you want to take new photos to enrich a certain portion of your video that's maybe not photo heavy enough. But specifically, I want to draw your attention to the onion skin. This is like a halo image. So this image that you're actually seeing here, these keys are not on the desk. This is just an after image of a previous picture that I had taken right here that's showing up. But this is in reality where the keys are on the desk right now. So toggling the onion skin all the way down will make it, you'll only see the onion skin, so you'll only see the previous picture, and all the way up, you'll only see the current picture. So having the onion skin somewhere in the middle gives you a good idea of the last picture you took and the amount that you want to change one picture to the next to get the effect that you're looking for your stop motion. Okay, I think that's all I want to say about that, and I will see you in class tomorrow.